Hey, y'all. So, as many of you know, I'm currently trying to break back into tech. I'm trying to get a software engineering job again. And a little bit about my background, I was a software engineer for over 6 years. And then I decided to just take a leap and dive really far into video, just see if I could learn how to make a really good video, especially like a social media video. And so I created over 200 videos for myself and for 5 different content creators and even one small business, and had a lot of fun doing that. But I think the next phase for me that I'm really aiming at right now is I just want to get a really solid software engineering job and just do very good work. And what do I mean by good software engineering job? What I mean is I want to be around on a team where there's people who are hungry and driven, and who I can learn from, and hopefully vice versa. And ideally, I want to be on a team that's really collaborative. You know, the last company I was at, before I left, I was at CNN, the large media org, for 5.5 years, and it was a very, very collaborative team. And I felt like I got to grow a lot and build a lot of cool things. And when I got stuck, it was a type of environment where you could just raise your hand and get help. And vice versa. If other people got stuck, I felt like I could help unblock them. So I'm looking for something like that, like a really collaborative place to work, but also a place where people are hungry and trying to really, really grow professionally. So that's what I'm looking for. And in order to get that next role, in order to find my next adventure, what I've been doing is I've been building personal projects, just trying to code almost every single day. And I've been taking this data structures and algorithms course, and occasionally zooming out and creating content on what I've learned or what I've built. So in this video, we're going to be covering Big O notation, and I'm just going to be giving a very simple explanation of Big O notation. I'm not going to go too crazy into the weeds, but just a very simple explanation of what is Big O notation and why it's important. So with that, let's get into it. So who is this video for? This video is for people who are comfortable with a little bit of JavaScript. So you don't need to be an expert, but if you just know a little bit of JavaScript, if you know simply like what a for loop is, what a while loop is, if statements, variables, all those types of things. If you've just written a little bit of code, I think this video is going to land a lot better than if you did not. But so that's who this video is for. Hopefully this will help you get an understanding of like a kind of big picture, conceptual, high level understanding of Big O notation, and then you can dive in deeper, play around. Maybe if you want, I can link you the course I'm taking, which I'm finding really useful. But yeah, let's get into it. So what is Big O? So Big O notation is used to tell us how efficient an algorithm is. And what do we mean by efficient? We mean how does it perform as its input grows? So let's just say, let's just do some live typing right here. Let's just say we have a function, and the function takes some array. It takes an array. So as the array grows, how does this function perform? If the array is only, 2 values, maybe the function performs really well. But what happens when the array is, let's just say 1,000 or 10,000 values? Does it perform just as fast? If it performs just as fast, that's amazing. That's what we would call constant time. But if it performs much slower, which it probably will, how much slower? And that's kind of what Big O notation tries to give us a handle on. And this is in terms of, speaking in terms of runtime. There's and that's going to run. We're going to focus on runtime in this demo, but just also know that you can use Big O notation to give you an idea of how an algorithm performs in terms of space complexity, which is how much space does it take on your machine? Like, does it take a lot of space, or does it take a little bit of space? Like, if you add a much bigger array, does it take up way more space, or does it still only take up the same amount? So, but we're going to focus on runtime, which is how long it takes to run. How long does this function take to run based on how big the array is? So let's look at this graph here, because I think this graph is really cool. So in an ideal world, you might have constant time. And remember, Big O is always looking at worst case scenario. So in an ideal world, whether you had an array of 1,000,000 values or you had an array of 1 value, it would perform the same. And you can see this green bar right here. It's always going to perform the same. whether it's a million or whether it's one, it's just going to do like one, or it's going to do like a constant number of steps. The amount of steps it doesn't really matter. Big O is looking at trends. We're not trying to find out like exactly how many steps. We're just trying to look at a trend. So maybe we have a function and this function does like 7 steps, whether or not maybe creates a variable and then it like logs a couple things and then it returns the first item of this array. And it doesn't matter whether the array is a million or 1 or 2, it just returns the first one. So anyway, that's constant time. Now, if O of n in this case, this blue line here, would be if it looped through each one, because we can see if it looped through, if we had a for loop that looped through each one, we're going to visit each value, and depending on how big the array is, we're going to have to visit more values. So maybe our function logs console logs every single value here. So if the array is huge, we're gonna have to visit every single array and console log every single one. And so the bigger it grows, the time it takes to execute is directly proportionate. It's O of n time to the n, the number of inputs it has. O of n squared would be even worse. Let's say we have like a nested for loop. We go through it once and we go through it again to do something else. For every increase in n, every additional value to the array, we're going to do 2 more steps. We're going to twice the amount of steps. So that's going to be much worse. And then I might do a different video on log of n, because that's actually pretty cool. There's like binary search trees and things like that are very, very like a little more like very, very often used because they're like log of n complexity, runtime complexity. But anyway, with that, that's a separate topic. But with that, let's get into some code. So let's just say we have this function. We were talking about a function, right? We have this function, and the whole goal of this function is to sum the last 2 numbers in an array. And we have this function here that's incredibly efficient. All it does is say like, okay, I'm going to find the last number of the array, and I'm going to find the second last number of the array. I'm going to sum them, and I'm going to return the sum. So we can run this code, and we can take a look at the results. We can take a look. See, it's just like 2 steps. Boom, boom. Like just 2 steps, returns, and we have 7, which is great. Just 2 steps. You can see like I or I guess maybe 4 steps. It creates 2 variables, sums them, returns the sum. Okay, that's great. But now let's look at this like less efficient one, which it's going to go through each item in the array and then says, if I come across the last item, assign it to number 1. If I come across the second last item, assign it to number 2, and then add. So now imagine this thing we're going to go through. We are going to be doing way more steps. We're going to be doing way more steps. And the amount of steps that we do as this array grows, the number of steps that this function has to do is going to grow. So let's just check this out. I guess I actually have to like replace the name. So we'll do sum last 2 less efficient. So we're going to go through, and you can just see, we're going to go through, and I'm stepping through. You can see we're just going through every single one until this if block works. And then we're like, okay, cool, we found it. And then it works. So and then we get the result. So as you can see, the first one is way more efficient. Our array, our input array, if this was like way longer, it would still be just as fast as if it only had 2 things in it. So whereas our less efficient one, if the array was, I don't know, like 1,000 or million numbers, it's going to be O of n. It's going to go through each one. So anyway, that is big O notation. This is another graph kind of showing the same thing. I like this graph better. Anyway, that's big O notation in my own words for now. And I hope y'all enjoyed it, and I will talk to y'all in the next one.